Hello everyone, welcome to my programming club. Today we will be solving another daily Leetcode problem, and the problem's name is number of dice rolls with target sum. So the problem statement goes like this: you are having n dice, and each die having k faces numbered from 1 to k. Given three integers n, k, and target, return the number of possible ways out of k raised to power n total ways to the to roll the dice so that the sum of the face up numbers equals to the target. So when you roll a dice uh, and the face up number comes and a number comes up on the top face of the dice, so the sum of those numbers on n dice that will be given to you should be equal to the target. You have to return the number of ways this can happen. Since the answer may be too large, you are asked to return it with modulo 10 raised to power 9, okay, plus 7. And let's have a look at the constants also. So k and n will be ranging from 1 to 30, and target will be ranging from 1 to 10 raised to power 3, or say 1000. So let's have a look how we will be solving this problem. To solve this particular problem, one approach can be a brute force approach, which you can try out all the possible combinations. Brute force approach. Try out all possible combinations. Okay. Total number of possible combinations, it's mentioned in the problem statement also, is this k and total ways. Here n and k are ranging from 10 raised to 1 to 30. So 30 raised to power 30. Number of operations will be order of 30 raised to power 30 number of operations will be required to try out all possible combinations, and this is very much greater than the 10 raised to power 8 operation limit. Basically, if the number of operations of your number of operations that your program will be requiring uh, exceeds or become equal to this operation limit, then you may get a TLE, and your solution will not be accepted. So in order to get your solution accepted, uh, we have to optimize this brute force approach. Now let's say there are 3 dice, or let's say 4 dice. These are 4 dice, and the target is something like uh, whatever be the target be. Let's say x is coming on the top face here, y, z, and let this be b. Okay, this is one sequence that is possible. Okay, one possible outcome. Another possible outcome can be uh, x, y, z. Up to here everything is same on as of the above outcome, and then let's say there is a little change here. The fourth dice face differs here and it becomes a. So as you can see, you will be doing calculations twice, once for this subproblem and once for this subproblem. So you will be wasting your time. If you could just have memorized the result for this particular subproblem, some computations would have been saved. Okay, so this particular property or phenomenon, let's say, is called overlapping subproblems. Okay, so this will be a major cause that you will be getting such high number of operations required for your program, because you will be doing recalculations again and again. So another property that can be observed here is part of this whole problem, solution of this whole problem depends upon the solution of this smaller subproblem. Okay, so we can say that solution of bigger problems can be derived from smaller subproblem solutions. Okay, so this is another observation, and this particular property, let me quickly change the slide, is called optimal substructure. Okay, and when these two properties are satisfied in a problem, then it is a valid candidate for approach that we use, uh, dynamic programming. It is essentially, those of you who are new to dynamic programming, it is essentially nothing but we store the result of smaller subproblems which frequently occur more than once, let's say, in a combination of possible outcome, and then when the same subproblem occurs, we need not to calculate it again. We just use the stored result for that, and we save some work or say computations. And also we use the solution of smaller subproblems to build up the solution of bigger subproblems. Okay, so this is what dynamic programming is. Those of you who are new to these properties and concept of dynamic programming, I will be providing link of articles describing these two properties, overlapping subproblem and optimal substructure, and a link for article explaining dynamic programming will also be provided to you. You can explore those articles and then you will be able to understand uh, it in a clear way. And for this operation limit concept also, I will be also providing a link of article describing uh, how the time complexity of accepted solution varies according to input size. Okay, so what optimizations we will be doing? We will first of all, to solve this kind of problems, you have to look what variables are determining your current state. Let's say you are at one possible outcome. Okay, and let's say here you can treat each of these uh, let's say dices 1 2 3 4 separately, and what you will do is, let's say on the second dice you are having some s1, then for this sum s1, what will be the contribution of previous states? By previous states I mean previous dice. let's say this is the nth dice. Okay, so you can only take contributions to this nth dice from the n minus 1th dice, because we are doing a running sum here. Let's say this was 1 2 3 and 4. Okay, and 1 plus 2 is 3 here. So you can also only take contributions from the previous uh, dice. So you may ask yourself that how could you have ended up with a sum of 3 with the contribution of previous dice. Okay, so you will see what was the number on the n minus 1th dice. This will be your previous state. Okay, and nth dice will be your current state. Now a thing here to be noted is that you can have only k options. Let's say you are having some s1, then you can be seeking out uh, combinations of s1 minus, let's say, uh, phase numbers, we call them. So phase numbers will be from 1 to k. So s1 minus phase number. Okay, and this phase number will be from which dice? N minus 1th dice. So these two variables will be determining your state. Current sum and the dice number. Okay, this is dice number and this is current sum. Okay, these two will be determining your uh, state. These two variables will determine state. Now you have found out which variables will be determining your state and how the current state will be depending upon the previous state. Let me write more clearly. So if you say you are at the nth dice and with some, let's say, s, then it will depend be taking contributions from all of the states, let's say phase numbers ranging from 1 to k. Then it will depend upon n minus 1th dice and s minus phase number. As long as this s minus phase number, let's call this previous state sum. As long as this previous state sum is greater than or equal to 0, you will be taking contributions and adding it to your current state. And let's say you are storing this result, so your equation will be looking like something like this, state transition equation, you can say. So this is pretty much it for this approach. And then what you will be returning? You will be returning nothing but result of since all the dices will be present in the sum that you will be doing. So n dices and whatever the target sum is given to you. Okay, you will simply return it and this will be your answer. Okay, so let me give you a recap. First of all, we have to find out what variables will be determining the state of your current state, let's say, and then you have to determine how the state transitions will be happening, or how you could have ended up in your current states. What will be your previous states that would will be possible and contributing to your current state. So this was your current state. Let me quickly change the color. Current state, and these were nothing but uh, your previous states. Finally, you will be returning your answer, which will be represented by this state, and dices and target sum. Okay, now let's have a look at the implementation. So this is the implementation. Here, if your target sum is 0 and your number of dices are also 0, then there is only one possible way to get this sum. So in that case, you will be taking the number of ways as 1 when the number of dices is 0 and also the target sum is 0. Okay, I have taken long here. You can also take int. I think it will not be much of a problem since you are anyway taking modulo. Then in problem statement we are asked to take modulo, return our answer with respect to modulo. So we are using modular arithmetic here. Then what we are doing is we are just filling our state result 2D array. Okay, this array will be representing various states that you will encounter while making choices for n dices. Uh, this is where you will store result for all the states that you will be encountering. And these all states will be comprising of two variables. State here will be comprising, pardon me if some spelling is incorrect, I hope it does not affect your understanding of the approach. State here will be comprising of two variables. One will be your current sum and another will be your dice number. Okay, so that's why we have taken 2D array. That's why we have taken a 2D array, or say vector. Okay, the number of variables comprising of a state uh, determines how the dimensions of your results storing array, or say vector, will be. Okay, so since there were two variables, so we are using 2D array or say vector. Okay, and then we are just filling our state result 2D array. For each dice number, you will be having various sums possible. Let's say on the third dice number we are having sum 3, and somewhere in some another combination we are having sum 4 in the on the third dice number. The sum here is running sum. Okay. uh, so this is nothing but the running sum. What I mean by running sum is that, let's say, the faces of dices are like x, y, z, and a. So if you are at this dice, let's say this is the third dice you are on, then your running sum will be x plus y plus z. Okay, we are starting from here and going in this direction. So then you will be taking contributions of the previous states and adding it to the current state. So the previous states, for previous states you will be seeing what will be the previous sum on one dice number previous. So let's say you are on n dice number, then you will be seeing the previous sums on n minus 1th dice number. This is dice number. Okay, this is also dice number, and this is your previous state sum, or you can say previous sum. Okay. One thing to be noted here is that it cannot be negative, so we are taking minimum of sum or k, whichever of them is minimum. Okay, and then we are just using modular arithmetic. At last we will be returning this state, which is n dices and sum equal to the target sum. N dices and sum equal to target. Okay. This will be the number of ways to achieve target sum with the help of n dices having faces 1 to k. Okay. So this is how we will be solving this particular problem. Those of you who are having any doubts or any queries in general, feel free to ask them in the comment section. Thank you for watching. Have a great day ahead.